All right, good afternoon, A4 Precalculus CP. This is Tuesday, June 2nd. We have two classes left for Precalc, this one and one more, and we are seniorless now. It's just the juniors. That's all right. We're still going to do some great learning even without the seniors. So, today, what I would like to do is I'd like to pretty much wrap up our discussion on trig equations. I'd like to show you two essential twists that you can put on these trig equations that are important for you to recognize and be able to work with. So, two little tricks that will come up with dealing with trig equations in general that are important. Going forward, a couple things. Yes, you will have a progress assessment this week, so make sure you do pay attention and take notes on this stuff because it will be the very end of what you will be assessed on. I do want to mention as well that if you did not get any of your previous progress assessments to me, please make sure you do that. I mean, some of the older ones I don't know if I can accept at this point, but particularly like the one that was due on Sunday or maybe the one from last week, please try to get those to me. I can still give you credit for, what you're able to do, and I don't want to take that away from you. I know it's a busy time. I know it's a time of uncertainty and a lot of unpredictability. So, I'm willing to be as accommodating as I can. Please try to get that missing work to me as soon as possible if you have missing work. The last thing I want to mention before I jump in officially is the fact that there is a summer assignment for students that are planning to take calculus next year, which I believe is most, if not all of you that are in this call with me right now. So that just like it was for entering pre-calculus, how you had skills from algebra 2 that you had to refresh on, it's the same deal for skills that are students that are entering calculus. There's some skills from pre-calc that you should make sure you brush up on. Now, the purpose of those summer assignments isn't to just make you spend your whole summer indoors or to torture you. It's not designed to take an exorbitant amount of time. It's really designed to serve as a refresher of your skills from pre-calc that will be built upon taking calculus next year. For example, trig, the sine, cosine, tangent, and all those properties, you better bet that those are going to come up in calculus. So if if you go all summer without taking a look at what the sine function does, and then all of a sudden you're in calculus and and you have problems with sine and cosine and tangent in them, you're going to be in a little bit of trouble. So that's why it's worthwhile to make sure you get that summer work done. Again, it's not something that's meant to torture you or take a crazy long amount of time. It's just something that is meant to serve as a nice little refresher. I don't know, I can't speak on what the structure of school will look like next year, whether it's going to be back to school as normal, whether it's going to be 100% distance learning like it is now, or if it's going to be some hybrid in the middle. But what I can say is that this past year, remember our first grade of the year was the material from the progress assessments, or from the summer work. It was a progress assessment on the summer concepts from the algebra 2 into pre-calculus summer packet. So I imagine for whoever you have for calculus next year, if you're taking calculus next year, then that will be probably the case for that class as well. Again, the summer work is only for the core classes, so Algebra 1, Geometry, Algebra 2, Pre-Calc, and Calc. If you're taking a Prob and Stats or Discrete Math or Financial Algebra or anything else, that is not necessary to complete that because it doesn't directly build off of Pre-Calc. Some of the stuff may come up, but it's not a direct translation like Pre-Calc to Calculus. All right? So just saying, make sure you get that work done. The tip that I offered to my Algebra 2 this morning and my A3 pre-calculus class just before lunch is you have these 3 days next week that are designed as intervention days or catch-up days. If you don't have any work to do, like you're all caught up in all your classes and all your missing work is turned in, I'd say bang out the summer packet. Just get that done and then you won't have to worry about it all summer. So I was a wicked procrastinator in high school, but even I think I would take advantage of that opportunity. So just saying, that is what I'd recommend doing. And if you have any questions on it, just feel free to let me know. But like I said, we only have 2 pre-calculus classes left, this and one more, so let's make the most of it. Does anyone have any questions on any of the information that I delivered to you just now? All right, then let's do it. So let's work on solving some trig equations. As we've done in previous classes, we saw that when you have a trig equation, what you really want to do is you want to get it down to, through probably processes from algebra 1, get it down to just a trig function equals a specific quantity, like cosine of theta equals 5, or 5 halves or something like that, or 2/5. can't equal 5/2, 2/5, or sine of theta equals 3/4, or something like that. Once you have that, you can then identify which quadrants your solution should be in. You can turn to your handy dandy calculator and you can work out what those specific angles should be by trying to find your first quadrant angle and working around the circle like this, whether you're in degrees or you're in radians. Okay? However, what we have yet to see is we've yet to see something like this. Let's try to solve for 0 degrees is less than or equal to theta, which is less than 360. So let's go in degrees from 0 to 360. And what if I gave you a problem like this? The secant of theta is equal to -5. Well, rats. You'd probably look at a problem like that and be like, secant? I don't know how to work with secant. Why are we working with secant? That's an ugly reciprocal function, right? Secant, cosecant, cotangent. Luckily for us, though, there is a trick that you can employ, a very simple trick using your identities below, to not have to deal with secant. You could recognize the fact that secant, remember, is the reciprocal of the cosine. And that being said, what you can do to both sides of the equation is take the reciprocal. Just like how you can add a number to both sides of an equation, or multiply a number to both sides of an equation, or square both sides of an equation, you can take the reciprocal of both sides of the equation and rewrite this as the reciprocal of secant is cosine of theta is equal to -1/5, the reciprocal of -5. Because if the secant of theta is -5, then the cosine of that same angle should be the reciprocal, -1/5. Now it works just like the other problems where I can turn to my handy dandy calculator. I recognize that the cosine of a negative angle, well, the cosine is negative in quadrants 2 and quadrant 3, right? I'll see what my calculator does for me. We're doing the cosine inverse of -1/5. It gives me 101.54 degrees, which if you notice is in the second quadrant. That's why I wrote it into that second quadrant spot. Now what I want to do is I want to find an angle in the third quadrant that makes that work as well. But first, what I need to do is find the first quadrant angle that matches up. So that way I can just translate it directly to the third quadrant. Yes, it is possible to go from here to here right away, but it's much easier, I think, if you always go back to the first quadrant and then you can just go bang right there. So we could work backwards a little bit to say if 180 minus the first quadrant angle should equal the second quadrant angle, I can say that 180 degrees minus the first quadrant angle should equal the 101.54. And then it's just a little bit of algebra 1. Subtract 180 from both sides, you get the opposite of theta is 101.54 minus 180, -78.46. And then if the opposite of theta is the opposite of 78.46, then theta is positive 78.46 degrees, which is your angle in quadrant 1. Given that information, you can now find your angle in quadrant 3 by saying, oh, it's just 180 plus that quadrant 1 angle. So it's going to be 180 plus 78.46 degrees, which if I go ahead and turn to my handy dandy calculator, I get that, 258.46 degrees. So those are my two answers, 101.54 degrees, which was obtained directly from the calculator, and 258.46 degrees. But that makes sense, hopefully, right? Using the reciprocal to just get rid of secant and now just treat it as cosine. We feeling good about that? If so, let's do another one. How about something like this? 4 times the cotangent of theta plus 5 is equal to 0. Okay? Well, once again, I don't want to work with cotangent. Before we take the reciprocal and turn it into tangent, though, let's get the variable by itself. So let's start with subtracting 5 from both sides, just like algebra 1. 4 cotangent of theta equals -5. Divide by 4, you get cotangent of theta equals -5/4. Well, if the cotangent of the angle is -5/4, then taking the reciprocal, the tangent of that same angle should be -4/5. Does that make sense to everybody why that's the case and how that works out? So now, knowing this, well, tangent is negative in quadrant 2 and negative in quadrant 4. It's positive in 1 and 3. So let's turn to my calculator. Let's see what that tells me. The tangent inverse of negative 4/5 gives me negative 38.66 if I round up. So negative 38.66 degrees, if you remember, is not within my 0 to 360 range, but we could just treat that as positive 38.66 because that's the angle in the first quadrant that's going to share that same tangent value. The tangent of positive 38.66 is positive 4/5. Okay? So by recognizing that relationship, we could say, well, let's just use this. And now let's take this and find the quadrant 2 angle and the quadrant 4 angle. The quadrant 2 angle would be 180 degrees minus that 38.66, which again, calculator, we got 180 minus 38.66, which is 141.34 degrees. And to find the angle in quadrant 4, we're going to do 360 minus that guy, so minus 38.66 degrees is, let's see, 360 minus 38.66 is 321.34. And those are our two solutions. If you notice that 321.34, by the way, would have been what you got if you took this angle right here and added 360 to go all the way around the circle and get to a coterminal spot. So a couple different ways you can do it. Any questions about that at all? Or are you feeling good? Feeling good? Hopefully? Yes? Alrighty, let's keep going then. So that's the sort of the first twist that I can throw at you, or that you'll see in these types of problems, is just show those reciprocal functions showing up along the way. But it's not really any cause for panic or confusion or chaos. All you have to do is just isolate the variable and then take the reciprocal of both sides to get it to a function you're comfortable with. Instead of working with cotangent, let's work with tangent. Okay, makes it much easier. The second twist that you can see in these types of problems is trig equations that involve some form of factoring. Oh yeah, factoring. Coming back from algebra 2. So something like this, for example. The secant squared of x minus 9 is equal to 0. Oh yeah, factoring. Coming on back. You may remember from algebra 2 if you had a problem like this. How about just x squared minus 9 equals 0? And you had to break that down. Well, that's a typical difference of two squares problem. You could factor that down into x plus 3 times x minus 3 is equal to 0, right? You remember that difference of two squares, you pretty much just take the square root of this and the square root of this. If this were x squared minus 25, you would be x plus 5 and x minus 5. X squared minus 64, for example, would be x plus 8 and x minus 8, right? The same exact thing can be done here. Instead of x, it's secant of x. So we're just going to say this would factor down to be the secant of x plus 3 and the secant of x minus 3. Everybody see that? It factors down just like you would in algebra 2. Going over here back to our algebra 2 example, this would then break into two problems where I'm looking for this little piece, when does x plus 3 equal 0, and this little piece, when does x minus 3 equal 0, right? Well, this happens at x equals negative 3, and this happens at x equals positive 3. The same sort of thing happens over here. I look for, in this piece, when does the secant of x plus 3 equal 0, and in this piece, when does the secant of x minus 3 equal 0? Okay? This gives us essentially two little equations to solve. If I subtract 3 from both sides, I get the secant of x equals negative 3, which of course we take the reciprocal and say that that's the cosine of x is equal to negative 1/3, which is an equation I'll have to solve for. And if I do the same on the right little expression here, I can add 3 to this side. I get the secant of x is equal to positive 3. Take the reciprocal, means that the cosine of x should equal 1/3. And now if you notice, it's pretty much looking for the same angle, or at least the same reference angle in all four quadrants. We're looking for when cosine is positive 1/3 and negative 1/3. It's taking that angle and going all the way around the unit circle. So this would give us something in quadrant 2 and something in quadrant 3 from this piece. This piece would give us something in quadrant 1 and quadrant 4 because cosine's positive here and because cosine's negative there. So I would start with the quadrant 1 angle, and then once you know that, you can just fill in 2, 3, and 4 by just starting here and going all the way around the circle. So that's exactly what I'm going to do. I'm going to start with the quadrant 1 angle to say, well, what's the cosine inverse? Whoops. Cosine inverse of 1/3. That's 70.53 degrees. So that's our quadrant 1 angle. And now let's just translate that all the way around. In quadrant 2, we can do 180 minus that 70.53. So quadrant 2 is going to be 109.47 degrees. Quadrant 3 is going to be 180 plus that. So 180 plus my 70.53 is 250.53 degrees. And quadrant 4 is 360 minus that. 360 minus 70.53 degrees comes out to 289.47. Okay? And so this particular problem has 4 solutions. Our 4 solutions being from quadrant 1, 70.53 degrees, quadrant 2, 109.47, quadrant 3, 250.53, and quadrant 4, 289.47. Pretty cool that in a difference of two squares problem with a little bit of factoring, it's actually, again, looking for that same reference angle in all 4 quadrants. Question about that at all? Pretty cool stuff. I got 2 more to show you today. All right, let's move on. How about a problem like this? Ready? If I had the sine squared of x minus the sine of x is equal to 0. Okay? Once again, these problems are really just glorified algebra 2. I'm now going to compare this to this problem. What if you had that problem in algebra 2, x squared minus x is equal to 0? Well, hopefully what you would do is you would take out a greatest common factor of x, leaving me with x minus 1 equals 0. And then this splits into 2, where we can say x is equal to 0, and from this piece, x is equal to 1, right? Because if I plugged in 0, 0 times this would equal 0, and if I plugged in 1, 1 minus 1 would equal 0, times that would equal 0. Same factoring can happen with the trig. I can say instead of pulling out an x, let's pull out a greatest common factor of the sine of x. Kind of just like you did with identities, if you remember. Leaving us with the sine of x minus 1 is equal to 0. That now splits into 2 little pieces. When is the sine of x equal to 0? And when is the sine of x minus 1 equal to 0? Okay? These are special quadrantal angles, so let's tackle this one first. When is the sine of x equal to 0? Well, if I look on my handy-dandy calculator, you can recognize that that happens at 0 degrees, right? At 0 degrees, you remember, because sine is your y, you are sitting right on that x-axis. So you could say, well, x equals 0 degrees. But when else actually is the sine equal to 0? What other angle has a sine value of 0? Well, not only is it 0 degrees, but it's also halfway around the circle, creating that semicircle, 180 degrees. So we have to make sure we note that as well, because 180 degrees also has a sine value of 0. And lastly, for this piece here, it's just a little equation you can solve. Add 1 to both sides. When is the sine of x equal to 1? Well, we know that. That's a quadrantal angle again. That happens when x is 90 degrees. Okay. So this little equation has 3 solutions. We get x equals 0 works, 180, and 90. Any questions as to why that's the case? The cool thing, too, that I didn't mention to my other class, I wish I did, is you could actually, when you have especially these angles like this, it's harder when you have just the generic, like, ones where you delve into decimals and have to use the graphing calculator, but ones where you specifically have your quadrantal angles or your special unit circle angles, you could actually take these, put them back into the function, and double check your work. If I actually plugged in 90, would you notice that what's the sine of 90 degrees? 1. 1 squared is 1 minus the sine of 90. 1 is 0. It works out, right? Plug in 0. What's the sine of 0? The sine of 0 is 0 minus 0 equals 0. Like, these equations actually do work out when you take these angles and plug them back in. You can feel free to do that with the decimals as well. It just gets a lot messier. All right, let's take a look at one more, and then we'll call it a day. How about the cosine squared of x minus 3 times the sine of x is equal to 3? Okay, how about something like that? Well, at first, you might look at this problem and you might be like, Mr. Giorgio, what am I supposed to do? I have cosine and I have sine. Like, I see the squared, so I can understand there's probably some factoring going on, but these are two different things. I don't really know how to deal with that. Well, using our identities, which you can see right below me here, you could actually rewrite cosine squared, and you could say, ooh, that's the same as 1 minus sine squared. Right? That's our Pythagorean identity. The cosine squared of x is the same as 1 minus the sine squared. So we can rewrite this problem as 1 minus the sine squared of x minus 3 times the sine of x is equal to 3. Now from there, it becomes a lot clearer as to what to do. Again, flashback to Algebra 2. Think if you had 1 minus x squared minus 3x equals 3. If I were teaching Algebra 2 right now, I would say we see x squared show up, which is a prime time indicator that we need to factor. But before we can factor, we of course have to set equal to 0. So I'm going to do the same thing over here. Given that the coefficient of x squared is negative, or in this case sine squared is negative, I would elect to move everything to the right to make that coefficient positive. Having a positive coefficient for that squared term helps make your life just way, way easier. If you notice, we never did factoring with a negative x squared. It's just ill-advised. Make it positive. So I'm going to move that over there. I'm going to add sine squared of x over this side. I'm also going to add 3 times the sine of x over to here. And I'm also going to subtract 1 over to here. So that gives me 0 is equal to, writing things in proper order, the sine squared of x plus 3 times the sine of x minus 1. Oh, sorry, not minus 1. 3 minus 1 would be plus 2. My fault. Right? We subtracted the 1 to move it over, but we got 3 that's already here. 3 minus 1 is positive 2. Now, just like if it were x squared plus 3x plus 2, I can factor that expression, factoring down with just x's. Hopefully you can see that I would need x and x to make x squared, 2 positives, and I would need 2 and 1 to make my 3 in the middle. The same exact thing happens here, just with sine of x instead of x. I have sine of x plus 2 and sine of x plus 1. Hopefully everybody sees that. Now that splits into 2 pieces. I can say, well, when is the sine of x plus 2 equals 0? And when does the sine of x plus 1 equal 0? Well, sine of x plus 2 equals 0. We can solve that one by saying the sine of x should equal negative 2. I can go ahead and use my handy-dandy graphing calculator and say the sine inverse of negative 2 is rats. Rats. What happened? A domain error? Why would that be an error? Oh, wait a minute. Think about that for a minute. The sine of x is equal to negative 2. The sine can't go any lower on the unit circle than negative 1, right? Isn't the biggest sine value positive 1 and the lowest sine value negative 1? You can't exceed positive 1 or go lower than negative 1. So this doesn't make any sense, as is supported by the calculator. You cannot have the sine of an angle equal negative 2. The lowest it can be is negative 1. So this little piece would produce no solution. Right? That little piece is not possible to satisfy. But there is still hope. this one might still give us something. Subtract 1 from both sides. I can see that the sine of x should equal -1, and that will work out, right? That's, like I just mentioned, our lowest sine value. That happens when x is 270 degrees. Okay? So again, remember that the sine of x is sandwiched between -1 and 1, right? If you take the sine of any angle, that value has to be between -1 and 1. The same is true for the cosine, right? The smallest cosine you can get is -1, the largest is +1. The same exact thing applies for the sine, where if you see something like this, where the sine of something is either bigger than -1 or bigger than +1 or smaller than -1, it just isn't going to happen. There's nothing that makes that work. Okay? But this little piece still had an answer to work with. Alrighty? This in calculus is actually a very important fact. It leads into something that's often referred to as either the squeeze theorem, that's how I learned it, or some people call it the sandwich theorem, because it kind of makes a sandwich, like these are the bread and that's the sandwich. I like the term squeeze theorem though. Essentially what it means is that if you can show that your sine value is greater than something and also less than that same thing, greater than or equal to something and also less than or equal to something, then it therefore has to equal whatever you were looking for. You'll do that next year in calculus, coming soon, next year, if you take calc. Okay? Anyway, quick little recap. So what we did today is I essentially introduced to you the last two little twists that you could put into these trig equations. The general solving process is still the same, so it's not like we're learning an entirely new crazy topic. But what we are doing is, first of all, noticing what happens if we deal with cotangent, cosecant, and secant. What about those reciprocal functions? Well, all we have to do is once we simplify down to just the function equals of value, same thing here, we could take the reciprocal of both sides to work with something that's much more comfortable. The other thing we could recognize is if there's factoring involved, like a squared term, well, any of that factoring would work just like in Algebra 2. Here we see a difference of two squares show up, but the trig version of that. Here we see a greatest common factor show up over there, just with trig. And here we see a more traditional trinomial factoring, like x squared plus 3x plus 2, trying to break that down. Same thing happens here. Okay? A big takeaway from this problem too is the fact that the sine cannot be bigger than +1 or smaller than -1, which is why that resulted in no solution. All right. I just want to quickly reiterate that there is going to be a progress assessment on this, so do make sure you ask me questions if you need to. I will post some practice problems on Classroom. If you have any lingering or missing work, I would like to get my grades mostly up to date by, tomorrow or at least the end of the week. So please make sure you get that missing work to me as soon as possible. I also want to mention the summer assignment again. If you are planning on taking calculus next year, there will be a summer assignment for you to complete. I'll also send that out to you via email today. I would recommend doing it in the next week when we have those 3 days. Just get it out of the way and get it done. I'll also be available if you need to ask me any questions, but that ball is entirely in your court. I want to thank you for your attention and focus today, and we'll make our last pre-calc class one to remember. Thank you, everyone, and have a fantastic day.
Thank you. You too, Mr. Giorgio.
See you later.